What specific problem does your method aim to solve regarding compositional generalization in diffusion models?
Our method aims to systematically investigate the factorization and compositional generalization capabilities of diffusion models, which have been inadequately explored in previous studies. Specifically, we address the lack of consensus on whether factorized representations in intermediate layers of diffusion models promote compositional generalization. By conducting extensive experiments on conditional denoising diffusion probabilistic models, DDPMs, trained on simplified 2D Gaussian datasets, we aim to clarify how these models learn to encode independent features and their ability to generalize beyond the training distribution. Additionally, we explore the impact of including explicitly factorized examples in training on the model's sample efficiency and generalization performance. Ultimately, our work seeks to provide deeper insights into the mechanisms of factorization and compositionality in diffusion models, enhancing their applicability in generating novel combinations of features.
How does the proposed method work? Illustrate it step by step through your experimental setup, including how you generate the datasets and train the diffusion models.
The proposed method involves a systematic experimental setup to investigate the factorization and compositional generalization capabilities of diffusion models. First, we generate datasets of n times n pixel grayscale images containing 2D Gaussian bumps, which are created by multiplying or adding 1D Gaussian stripes at specified mu_x, mu_y coordinates on a finite canvas. The training dataset is constructed by enumerating all possible Gaussian configurations with varying parameters, such as the spread, sigma_x, sigma_y, and increments, d_x, d_y, resulting in a dataset that can be adjusted for sparsity and overlap. Next, we train a conditional denoising diffusion probabilistic model, DDPM, using a standard UNet architecture, where each image is paired with a ground truth label, mu_x, mu_y. During training, we assess the model's performance by evaluating its ability to generate accurate images based on these labels, while also analyzing the learned representations through dimension reduction techniques like PCA or UMAP. Finally, we conduct experiments to test the model's compositional generalization by training it on datasets with isolated factors of variation and a few compositional examples, allowing us to observe how well the model can generate novel combinations of features not seen during training.
Can you provide a simple example illustrating how your method achieves compositional generalization, particularly focusing on the generation of 2D Gaussian bumps in your experiments?
In our experiments, we illustrate compositional generalization through the generation of 2D Gaussian bumps by training the diffusion model on datasets that include isolated factors of variation. For instance, we trained the model on a dataset of 2D Gaussian sum of stripes, SOS, while deliberately excluding certain Gaussian SOS from specific test regions. When tested, the model demonstrated the ability to generate Gaussian SOS centered in these excluded regions, effectively combining the learned features of the training data to produce novel outputs, such as generating a Gaussian SOS at coordinates that were not directly observed during training. This ability to generate new combinations, like producing a Gaussian bump at a previously unseen coordinate, exemplifies compositional generalization, as the model can create outputs based on the independent features it learned, even when those specific combinations were not part of the training dataset. Thus, the model's performance in generating these bumps confirms its capacity for compositionality, as it can combine learned features in novel ways.
What are the practical benefits of using your proposed method compared to existing approaches for understanding factorization and compositionality in generative models?
The proposed method offers several practical benefits over existing approaches for understanding factorization and compositionality in generative models. Firstly, by utilizing a low-dimensional dataset of 2D Gaussian bumps, the method allows for a clearer analysis of the model's learned representations, facilitating the identification of factorized versus coupled representations. Secondly, the incorporation of explicit cognitive tasks enables a dual evaluation of both the model's generation output and its intermediate layer representations, providing deeper insights into the mechanisms of compositional generalization. Additionally, the findings indicate that training with isolated factors of variation alongside a few compositional examples significantly enhances data efficiency, allowing models to generalize effectively with fewer training samples. Lastly, the connection drawn between manifold learning and percolation theory offers a normative framework for understanding the emergence of compositionality, which could inform the design of more effective training strategies in complex datasets.
What specific validation methods did you employ to test the effectiveness of your approach, and what metrics did you use to quantify the performance of the diffusion models?
To validate the effectiveness of our approach, we employed several specific methods, including persistent homology, to analyze the topological features of the learned representations and orthogonality and parallelism tests, to differentiate between coupled and factorized representations. We also conducted experiments where we trained models on datasets with varying configurations, such as 2D Gaussian SOS data and 1D Gaussian stripe data, to assess their compositional generalization capabilities. The performance of the diffusion models was quantified using accuracy metrics, specifically measuring the correctness of generated images in displaying the center location of the 2D Gaussian bumps. Additionally, we analyzed the effective dimension of the learned representations through the participation ratio, which provided insights into the dimensionality of the model's internal representation during training. These methods collectively allowed us to assess the model's ability to generalize beyond the training distribution and their data efficiency in learning compositionality.
What were the most significant results obtained from your experiments, particularly in terms of the model's abilities to compose and interpolate features?
The most significant results from our experiments indicate that diffusion models excel in compositional generalization but struggle with interpolation. Specifically, we found that given factorized continuous conditional inputs, the models learn hyperfactorized representations that are orthogonal for independent features, allowing them to compose well but interpolate poorly. When trained on datasets with isolated factors of variation, the models demonstrated remarkable data efficiency, requiring only a few compositional examples to generalize effectively. However, they exhibited limited interpolation ability, as evidenced by their performance in generating outputs in overlapping test regions, where they could generate one feature accurately while failing to do so for the other. Overall, our findings suggest that while the models can compositionally generalize when exposed to the full extent of independent latent features, they do not learn a fully continuous representation across those features.